Bismillahirrahmanirrahim. Assalamualaikum dear students. Today our lecture is about basic groundwater hydrogeology. It is a continuation of the previous lecture in which we try to explore what our subsurface strata constitutes of. In that lecture we found out that there are basically two major zones, vadose zone and saturated zone, and then we characterized them based on their constitution, what it constitutes, and then we try to find out what the major particles do exist in those medium, and then today we will continue with the same topic, and we will further explore what our subsurface is formed of, what it has the configuration, how it is going to behave when some new material is entering into the system. So in the previous lecture we worked on the sources of contamination: point source, non-point source. So is it clear what is point source and non-point source? So point source is something which has a very specific and defined source of contamination. It's like drains, it's like our pointed source, like which constitutes of our dump sites. So what are the non-point source? Non-point source cannot be identified. It cannot be traced back. What is the source of the contamination? So the best example is our agriculture lands, and the source of pollution in that is our pesticides, fertilizers. All these things are being spread out along with the surface flow, so we cannot trace them back. So in case of point source we have a channelized flow, while in case of non-point source we have a sheet flow. So the point source is like a line, like a formation of carrying the waste, carrying the pollution. Non-point source has a surface area to carry the pollution. Then we studied subsurface strata containing soil and groundwater, vadose zone with its properties. Vadose zone is actually consists of different layers, and every layer is behaving differently because the characteristics are different, the particles are different, and then finally their behavior is different. Now saturated zone is again, it is having some geological formation, which is actually depending upon the material of which those geological formation constitutes of, whether it's rock fragments or some silt or sand or clay, whatever it is. Based on that we will be defining the saturated zone. Today again we will continue with this topic. We will further find out what geological formations are made up of. And then we have pressure distribution in both zones. I think it's quite difficult to understand how our pressure is varying in both the zones, vadose as well as saturated zone. So we will continue with this topic as well. So it depends upon the geological formation of subsurface. So what kind of strata it is, what kind of water table level it is, whether it is a phreatic zone or it is having a piezometric pressure. Then we defined capillary fringe, burst zone, atmospheric pressure at water table level. All these things we discussed in the previous lecture. Subsurface characterization. So soil is the basic component which has different types, like it has boulders, silts and sand and rock fragments and clay. So all these things have different characteristics, and especially how they are combined together in a particular specimen or in a particular volume of soil. So that actually defines the behavior, how that volume of soil will behave when some water will filtrate or some contaminant will filtrate into that volume. So then we need to understand those properties of soils. So those are actually linked with the hydraulic conductivity, permeability, and then we are also concerned about the grading of the soil and then sorting of the soil. So all these things are important to describe the movement of water through a typical soil layer. And further, if we go in the particle size distribution analysis, we have a hydrometer method. I think you will do it by yourself in your practical part. Then we have grading and sorting. We will again explain these things. Behavior of soil when contaminant enters soil medium. So it was very briefly introduced in the previous lecture. We will explore it in detail in our coming lectures. Today our focus will be on groundwater hydraulics. So geological formation is important for us. The groundwater storativity is important. The movement of water is important. Under what principle and processes the groundwater is moving in different directions. So what actually makes the water moving? So what are the driving forces of water? How, in which direction water will be moving? So we can determine it. So we will be exploring all these things in this lecture and as well as in the next lecture. This is something about a very brief introduction about the subsurface strata, again like previous. So we have a groundwater surface, we have a vadose zone which is coming all the way to the water table level. So water table level is actually separating the vadose zone and the saturated zone. And then we have a water table level, and this water table level is phoretic or unconfined aquifer. Then we have a saturated zone which is limited by the confining band, and then we have a confined aquifer or artesian aquifer. We will be defining it in the coming lectures. So this is a typical volume of soil in a unsaturated zone. So what it actually, that volume of soil is consisting of? It is consisting of solid particle, the most important thing. Then the remaining part is constituting of water and air. So if we have 100% volume of volume covered with water, it will be called a saturated zone. But normally in our unsaturated zone we have both water as well as air. So how we will be measuring these things? Actually this is the basics. We will be defining our solid particle as an important section which will be related with the contaminant adsorption with this solid particle. So just to give you an idea, whenever our contaminant is entering into this volume of soil, it is either going to react with this water and getting dissolved in this water, and it will be traveling along with this water into the subsurface, joining the groundwaters, or it will get attached with this solid particle. So if this contaminant is getting attached with this solid particle, then it is going to be retained in this volume of soil. That means that it depends upon the characteristic of that contaminant, how it is going to behave. Whether it is going to get attached with this solid particle or it is going to end up in this water. it is going to be dissolved in this water. So again, this water has two characteristics: whether this water is going to be retained here and getting stuck up. So it is normally due to the particular behavior of this volume of soil. So whether if this volume of soil is having a graded soil, you know what is graded soil? It is graded soil. It is that kind of soil which has a variety of soil particles. It has silt, it has clay, it has sand, gravels, everything is there. So because of all the mixture, there will be a lot of hindrance in the movement of water. So the water will be actually retained in the soil. In that case, the sum of the water will be stored here, retained here, and then some of the water will be moving freely, because you cannot capture all the water. If there are pores, the water will make its way down into the soil and then into the groundwaters. So it is important to understand the nature of this volume of soil, how it is going to behave. Then in next important thing is how we are going to describe it. So for us, we need to understand the fate of the contaminant. So firstly, the water, there are three possibilities: whether the contaminant is going to get attached with this solid particle. So what are the characteristics which will be ruling this action, this process? And that characteristic is the nature of this solid particle. Secondly, nature of the entering contaminant. If this solid particle is consisting of clay, that means this clay is going to react with anything coming inwards and which is going to have a charge on it, and it is going to react with this. So second option is the contaminant is entering. It has nothing to do with this. For example, there is if it is clay, then most of the cases clay is considered as a negative charged particle. Anything coming positive will react with it and get stored in it. Get retained with it in forming an ionic bond. But if this solid particle has not the capacity to react with the incoming charge of the contaminant, then that contaminant will be reacting with this water, and that means that this water is going to either take it down to the soil and groundwaters, or it will be retained based on the overall formation of this volume. So please focus on this concept of behavior of the contaminant in the soil. We will further study it in detail in our coming lectures. But just to give you an intro, it was just a brief introduction that all these things are important when we are talking about the fate of the contaminant in soils and groundwaters. Well, one more thing. We need to understand the concentration of water, and then we need to understand the mass of contaminant which is attached with this particle. It is supposed to be measured in this unit, grams per kilogram, because this is the mass of the contaminant, this is the mass of the solid. So this will be giving us the contaminant concentration which is attached with these solid particles. One more important thing, just for the sake of revision, when we are studying the complex soil structure beneath the beneath the ground surface, we must understand all types of properties of soil which can exhibit under the ground: anisotropy, heterogeneity, and dispersion behavior, then linear and non-linear behaviors of soil. All these things are important to describe the phenomenon, how the contaminant is moving in different layers of the soil while it's traveling down. So anisotropy is the behavior and characteristics of the soil which are changing in different directions. Can you understand this phenomena, anisotropy, how it is going to behave? So for example, we are only considering one point, and that one point will be behaving differently in the direction downwards, in the direction horizontal, and in the lateral direction. So if it is behaving differently in different directions, then it is called anisotropy. While heterogeneity is layer to layer variation of the characteristics of a particular soil mass. So it is again obvious that when we will be having a complex soil structure, there will be higher values, higher significance of the heterogeneity. Soil will be no more uniform, it will not exhibit similar characteristics in the different directions, whether it's lateral or it's longitudinal. Then we have another important thing, lateral and longitudinal dispersion. So as we talked in this case, that our pores are important. We have the contaminant here with the water, or we have the contaminant here with the solid. Then it's important that we understand how the dispersion can take place. So dispersion is actually the separation of the solid particle, the separation of the contaminant from the water, and it will be behaving differently because we are having different natures of the layer. So every layer is having its own hydraulic conductivity. So that hydraulic conductivity will depend upon the pores, and those pores will depend upon the particle size distribution. So first consider one layer with sand, second layer is with silt. Both have different hydraulic conductivities. So that means the dispersion of the water along with the contaminant will be different in these different layers. Then we have a linear and non-linear behavior of soil. It is more linked with the compaction issue, the stress and strain relationship. So if we are having a stress and strain relationship which is directly proportional, that it means that there is no significant stability of the soil. As the more the stress, the more the strain. So that means the soil is not predictable for the stable structures. It is going to collapse. So it is again important to understand the subsurface behavior. Now again the gradation, I think it's quite obvious. You have gone through it. We will not spend much time. But an important thing is that in case of gradation, we have a distribution of the particles, and all kinds of particle sizes are existing. So normally the voids are filled up with the finer particles. So that means the voids are lesser. If we have lesser voids, that means the permeability of their soil is less. So if there is less permeability, that means the movement of contaminant is less. So normally that's the reason we have a lined canal with the particles which are more graded, and they have lesser permeabilities. Sorting is something to be done with the same size of particles. Again, it is important while we are dealing with the lining of the canals and lining of the wastewater treatment plants, because we are normally do this kind of lining with the clay layer, and that clay layer has the least permeability. Then we have these things. I think you can go through by yourself. This is again something being repeated. You can go through. So the meadow zone is the term, the unsaturated zone, and so this phreatic zone is actually showing that our subsurface our groundwater is having an unconfined zone. We will see what is unconfined zone. Capillary fringe. So there was a term perched zone. What is a perched zone? It is that volume of water which is sustained in the topmost layer, and here somewhere in the unsaturated zone we can have a perched zone with the bedding of the hard rock or something which is hindering the movement of water. So we can have a water storage here, but that water cannot be drained or it cannot be discharged. And so this is the same. So the volume of soil particle which we studied earlier is shown here in detail. So we can consider this is the solid particle, this is the water with this is the part with the water, this is the part with air. Both these are making the wide volume of voids, volume of pores, both. And if we are going to find out the porosity, it will be the volume of pores over the total volume. So this will give us the total availability in which water is going to be passed through. So then some of this water, capillary water plus absorbed water. So Vp is equal to the volume of pores in which we are having volume of the capillary water, and then this water cannot be drained. So this is the water which is gravity water, and this water can be drained. This water is going to retain, this water is going to move forward. So this is the total volume in which Vp is the volume of pores, and then this is the volume of solids. Volume of solids and volume of pores. So next is so if you see this VG section, this VG section is showing us the volume which is going to travel, which is going to move, which is going to be drained, and this water is actually providing us yield. So that's why when we are going to find out specific yield, we are going to have the ratio of this part over the total volume. Here are the definitions. I think you can go through both, and the important thing is that specific yield plus specific retention are going to give us the porosity. So this is actually the specific yield, this is the specific retention, and both of them are actually present in the voids, but this water cannot be drained, only this water is to be drained. Here is the groundwater. What is the source? Of course, it is well known. It's from the infiltrate, and then these are the systems and some of the interceptions. You can go through it. So if you check it here, the groundwater occurrence, we are concerned with the significance of the mobility and retention for soil and groundwater contamination. We just checked how a volume of soil is going to behave when a contaminant enters in that volume. Then we have based on the nature of soil texture, geological formation and contaminant nature and its behavior in the soil and groundwaters. So if you can again, it is as we talked that what that solid particle will constitute will define the fate of that contaminant. If it's clay, it is going to absorb the other charged particle. If it is sand, it does not have any charge. It is not going to absorb any contaminant with the sand particle. So it will. This is how we can determine that how much the storage of groundwater can be obtained based on the characterization of the soil. So that's why I was earlier explaining to you that the site characterization normally consists of the understanding the behavior of the soil and studying the nature of the soil, and then how the contaminant will travel along with the water. All these things are important while characterization of the site. So these are something again which is I think well explained already. So again, zone of saturation, zone of aeration, and in this zone of aeration, which is called Veros zone as well, we have a capillary zone, we have an intermediate zone, we have soil water. So it is the repetition, I think, sorry. So these are the definitions you can go through. These are the measurements, I think, well explained. And porosity is the ratio between the volumes, so it will be not having any this unit. This is actually the volume of void, and then this is the total volume, and we can simply divide both to get the porosity value. So what is the yield? The portion of groundwater drained under influence of gravity is called specific yield. Portion of groundwater retained as a film or rock surface with very small openings is called specific retention. So then this is responsible for the yield, and this is responsible for the retention. And these are the definitions, please go through. So here you see the soil, and then clay, then sand, gravel, limestone, sandstone, granite, and basalt. So you check the porosity, and then you check the specific yield, and then you check the specific retention. Porosity is this is the volume of void. This is the volume of gravity water. This is the volume of retention. So the combination of both will give us the porosity. So if let's take the example of clay, it is going to have 50 porosity, but the specific yield is only 2 and specific retention is 48. So it means 48 parts is going to be retained, while only 2 parts will be passed through that. The reason we talked about is what we talked in the last lecture. It is based on the very minute level of the voids in case of clay. There is no space between to have more retention, and especially because the voids are very small, the water is going to create a surface tension. Because of that surface retention, the water is going to get clogged and it is not going to move downwards. While in the case of sand, you can see that the porosity is only 25, and it is having maximum yield with minimum retention, that is 3. So here is some explanation. We have a variety of the particles on the x-axis and the percentage is on the y-axis. So this is the retention. Specific retention is equal to porosity minus specific yield. So I think you can go through it by yourself. So these are again the definitions. Storage coefficient is the storativity, and it's the volume of water which an aquifer releases from or takes into storage per unit surface area per unit change in the head. So something which is going to be available in the aquifers will be declared as storativity S, and for unconfined aquifer it is S is equal to SR, which is the retention. So transmissivity is the reverse, and in this case we are more concerned with the hydraulic conductivity. So and this is one of the parameters, and when we will multiply it by the thickness of the aquifer, it will give us the transmissivity of that layer or aquifer. So this is the expression K into B for the determination of transmissivity. So zone of saturation we have already discussed. It is the about the upper zone, normally constituting of the unsaturated zone, and in saturated zone we have the water under hydrostatic pressure, and similarly when the water is rising against that hydrostatic pressure, it will create a negative pressure in the zone of aeration. So what are the aquifers? So let's continue with this in the second part of the